So let's just review some of the facts about cyclotomic number fields, and these are facts that make number fields, and in particular cyclotomic number fields, so nice to work with. So let's start out. So we'll start out with zeta m, a primitive mth root of unity, and we'll let k sub m be equal to q adjoint zeta m. I guess what makes cyclotomic number fields so nice is that they're so explicit, in the sense that, you know, a lot of the things that are kind of a mystery for general number fields, you actually know in a cyclotomic number field. For example, the ring of integers in a cyclotomic number field, you know that it's actually just z adjoint zeta m for q adjoint zeta m, right? And the same, we also know exactly what the Galois group is. The Galois group is just z mod mz star. Okay, it's isomorphic to z mod mz star. And we also know things about the decomposition of primes, moving primes from the integers up to z adjoint zeta m. For example, we know that p ramifies in km if and only if p is a divisor of m. We also know things about the Artin automorphism for cyclotomic number fields. If p isn't a divisor of m, then the Artin automorphism is well defined. We can actually figure it out. And we actually know it explicitly. It's just the math that takes zeta m to the p. And finally, if f is the p order or the m order of p, in other words, this is the smallest integer such that p to the f is congruent to 1 mod m, then this tells us that the ideal that p generates in z adjoint zeta m is a product of r prime ideals, where r is phi of m divided by f, and the degree of each of these extensions, like each of the residue class fields, is also just f. So yeah, this is very nice in the sense that we kind of know, well, we know a lot of things, right? And in particular, we know exactly kind of how primes, right? We know how primes kind of behave as you push them up from z to z adjoint zeta m. And this is kind of one of the main goals of, you can think about this as being one of the main goals of algebraic number theory. I mean, you kind of want to know what is the behavior of primes as you move them up various extensions. And you also want to know kind of vice versa, how does the behavior of primes, how does that kind of affect what kind of an extension you're looking at? So this is kind of the topic of class field theory. And the more you know about how primes decompose, the better off that you're going to be. And the fact that we know exactly, the fact that in cyclotomic number fields, the fact that the behavior of primes are basically, you know, the behavior of any given prime is basically determined by its congruence mod m, is a very, it's a very nice fact and makes these things very nice to work with. And I guess also the nice thing about cyclotomic number fields is not only that they themselves are so explicit, but they exert a great deal of influence over abelian number fields in general. This is via the Kronecker-Weber theorem. Right? So
extensions of Q, right?
Right. So you take any extension, take any abelian extension of Q, it's going to have to be contained in a cyclotomic extension, something like this. And the fact that this is so explicit allows you to say explicit things about abelian fields in general. So they're very nice in that regard. Not only just because of themselves, because they're nice to work with themselves, but because they exert this great deal of influence over the theory of abelian extensions.
And there is no such analog.
Right, and this is right, and this really only works over Q, which is kind of the amazing thing. I mean, there is you can actually get kind of some explicit class field theory, so to speak, over imaginary quadratic fields. So this is a theory of complex multiplication. But in general, it's very, you know, it's not really in the number field setting. Getting this explicit class field theory is actually quite difficult, because it's nothing so nice is currently known. But you wonder, in the function field setting, can we be so lucky as to find something so nice as this? And how much influence do these kinds of constructions have over, say, well, you know, over classifying, say, extensions of say of any given function field, right? So what we're going to be interested in today is maybe deriving an analog of cyclotomic number fields in the rational function field setting. So yeah, and then the explicitness of cyclotomic number fields, it doesn't just end here. You know, the fact that they're so nice to work with, it leads you to other topics such as like class number formulas. There's actually class number formulas for cyclotomic number fields, and there are explicit annihilators of the class group. These are called Stickelberger elements. All kinds of nice explicit results for cyclotomic number fields. And again, maybe even the larger part of the game is trying to figure out, you know, how much of, by virtue of the fact that every abelian extension of Q is contained in such a field, is contained in the cyclotomic number field, how much of that explicitness then bleeds down into the general abelian extension setting. So yeah, so long story short, this is all very kind of valuable stuff to know. And we want to know what is the function field analog of this kind of a thing. Okay, so if we want to know, I mean, what is the right analog in the function field setting for, say, integer, and what is the function field analog for, say, rational field? Well, so let's let FQ be a finite field with Q elements and its characteristic P. And so I guess in the number field land, what we have is that the normal, regular old integer z, they sit inside Q. The Q is the fraction field, I guess, of z. And all the stuff that we were talking about before, all this kind of the cyclotomic, I guess the structure of cyclotomic number fields, it kind of relies on adjoining to Q what? I guess the z torsion, if you think of z as acting on the algebraic closure of Q just by exponentiation, you could think of, cyclotomic number fields then arise by adjoining torsion elements, z torsion elements from the algebraic closure of Q to Q. So this is how you kind of generate these fields. So if we want an analog of cyclotomic function field, then I guess what we really need is we need an action on, first I guess we need to understand what are the analogs of these two guys. Well, it seems like the right analog for z is the polynomial ring FQ adjoint T. And this is for a number of reasons. One of which is, both of these guys, FQ adjoint T and Z, are both unique factorization domains. In fact, they're both principal ideal domains. In fact, they're both Euclidean domains. So that seems to be a pretty tight analogy, FQ adjoint T to Z. And then, of course, the fraction field of FQ adjoint T then is the rational function field with coefficients in FQ.
Also finitely many units. What's finitely many units?
Ah, right, yeah. So both of them also have finitely many units. Right. So A is going to be our analog for Z, and K is going to be our analog for Q. All right, so if we want an analog of cyclotomic function field, perhaps one should look for an A action on, say, the algebraic closure of K. So A acts on, let's just say K bar, where this is the, so this is the separable algebraic closure. So, but anyway, so yeah, we want some sort of an action on the algebraic the separable algebraic closure of K that in some sense mimics exponentiation. And, so, what the hell is that? So, how do you actually exponentiate an element of K bar by a polynomial? We need a way of defining this. And from the outset, it's just not all that, it's not clear exactly what that analogy should be at all. So as it turns out, we can actually, there actually is an analogy to be drawn. So let's discuss that. So with the benefit of a lot of hindsight, and hindsight among other things, as it turns out, we can we can define this analog of exponentiation by polynomials in the following way. So let's let K adjoint tau be the twisted polynomial ring, where tau, it's actually the map. You can think of tau as being associated to x to the q, or tau being the map that takes x to the q. So then the twisted polynomial ring K adjoint tau is one where you have the following commuting relation. So for all a and k, tau a is actually equal to a to the q times tau. And the reason, so we'll get to, maybe we'll talk in a second about why this weird commuting relation is the way it is. But let's let C be the FQ algebra homomorphism defined by mapping T to T plus tau. And remember that A is generated as an FQ algebra by T, so it suffices to actually just define what happens to T. And then you can extend, since this is an FQ algebra map, we can just extend kind of by linearity to the rest of A. So for short, we're going to write C sub m for C of m. And just to write out an example, we have, say, C sub t squared. This should be t plus tau times t plus tau, which when you write it out, well, we get t squared, just foiling, right? And get t times tau, so that's coming from there. And we get tau times t, so that's the same thing as t to the q times tau, so that explains this guy, and then tau squared. And so yeah, getting back to what I said before, I mean, this funny commuting relation that's coming from the fact that we really want the multiplication in this ring to kind of mimic function composition when we're kind of thinking of tau, when we're associating tau with x to the q. So just kind of rewriting this line just kind of in the other way, we could write this as tx plus x to the q composed with tx plus x to the q. That's really what we want to get out of this. And then when you write out exactly what this is, you wind up getting kind of the exact same thing when you're associating tau with x to the q. So anyway, now that we have this map is called the Carlitz module. This map is actually the thing that tells us exactly how, or winds up being just the right analogy to describe kind of exponentiation by polynomials. We can think of A now as acting on k bar by m acting on any given m and A acting on some lambda and k bar is defined in the following way. M acting on lambda is just C sub m evaluated at lambda. So for example, suppose m is t squared, then m times lambda, or m acting on lambda, would be like t squared times lambda plus t to the q times lambda to the q plus lambda to the q squared. So, and this turns out to be just the right analogy, in the same way that the integers act on the algebraic closure of Q by exponentiation. Our integer polynomial ring A is going to act on k bar in this fashion, and this winds up being just the right analogy that we need. Just the right analogy so that, just the right analogy so that when we adjoin kind of torsion points of this action to our base field K, we wind up getting things that look a lot like cyclotomic extensions. So speaking of which, let's talk about how that analogy actually works. Okay, so now that we have this Carlitz action, or we know the right analog of exponentiation in this function field setting, and what I mean by the right analog is the analog that, I guess in some sense, well, so what? I mean, you could look at the you could kind of look at the case of cyclotomic fields, and you could say, well, cyclotomic fields, the way to generate a cyclotomic field, or the way to generate a cyclotomic field over Q, is to adjoin some torsion element of the action of exponentiation of integers on algebraic numbers. So the torsion elements then would be something like, they'd be the things that when you raise them to a certain power, they get back to 1, so in other words, the roots of unity. So the Carlitz action on k bar is the right analog of exponentiation in the sense that, well, if you define, so pick some m in A, and look at the torsion, the m torsion points of k bar. As it turns out, if you adjoin these elements to k, then this winds up giving you the right analog of a cyclotomic field. So yes, let's start this. So we'll let lambda sub m, let that be the torsion points, or the torsion elements with respect to m. So all the lambdas in k bar, such that the Carlitz action of m on lambda is 0. Then we could show that lambda m is an A module with our Carlitz action. And in fact, we actually know that lambda sub m is isomorphic to A mod ma as a A module. And this basically is a kind of an augmented. I mean, really, this kind of follows from the theorem on finitely generated modules over a PID. This is essentially just an augmented version of that, or kind of an enhanced version of that is where it comes from. But anyway, the proof is actually the proof is basically a quotation of that theorem plus a little bit more stuff. But anyway, so lambda m is an A module. Again, I'm saying it's an A module. I'm saying it's an A module with respect to the Carlitz action. So A acts on lambda m kind of in the Carlitz way. Okay. So we know that lambda m is an A module, and in fact, lambda m is isomorphic to A mod MA. And this is kind of analogous to the situation where, well, I mean, yeah, if you look at what is the analog of lambda m in the number field setting, well, it would be mu m, the mth roots of unity. And in the same way, we know that the mth roots of unity is isomorphic to z mod mz, right? So this is starting to look pretty good. Right, and then we're going to let k sub m, we're going to let that be k adjoined lambda m, these torsion elements, and that's going to wind up being our analog of q adjoined zeta m. Okay. And when you start looking at all this stuff, you wind up, it's not too hard to realize that if you look at the Galois group of k sub m over k, this winds up permuting these elements around and fixing the base field in the same in the number field setting. And considering this this identification, you realize that there's an injection of the Galois group into the Galois group of Km over K into GL A mod MA, right? In other words, yeah, if you start permuting things or these things around in some linear fashion, then you're going to do that over on the right hand side as well, right? So so we can make this injection, and this guy is isomorphic to A mod MA star. That's just a kind of a simple thing. And this is kind of, this is very analogous to the classical, or to the number theory, or the number field setting, right? So we have an injection of the Galois group from K joined zeta m over Q into Z mod mz star, the same way we have here. And in fact, we actually know that this is an isomorphism, and with a little bit more toil, we can figure out that that's an isomorphism as well. Okay. So very, very analogous situations. And so now let's talk about exactly how this analogy, how does this analogy work? And the way it's going to work is that K adjoined lambda m is going to be an analog. Well, I guess we already see that it's an analog in this fashion, but it's also an analog in the way that primes behave when you take irreducible polynomials in the rational function field and you push them up into this extension. The behavior of primes is going to act very, very similarly, almost identically. It's almost like you're talking about the same thing. It's that similar. So it's more of an identification than it is an analogy. So. Okay, so let's talk about that next. Okay, so so like I was saying before, this Carlitz action is the right analog of exponentiation in kind of this sense, in the sense that when you look at these torsions, when you look at lambda m and you join the elements of lambda m to k, you get something that behaves identically to a cyclotomic extension. And so, for example, let's let little lambda m be a generator for big lambda sub m. And we know that it's cyclic because, again, it's isomorphic to A mod MA. Then, yeah, so if you take any polynomial A that's co-prime to m, then C sub A of lambda m over lambda m, this is going to be a unit of OM, basically the integers of Km, okay? And another thing we know is that we actually know these integers explicitly. It's just A adjoin one of these torsion elements. This is exactly analogous to the situation in the number field setting, where we have 1 minus zeta m to the A. This is like the action of exponentiation divided by 1 minus zeta m. This is a unit of Z adjoin zeta m star, and we know that the ring of integers of Q adjoin zeta m explicitly, and it's nearly the same. I mean, it's a very analogous type of thing. Right, and we know that pick a prime, an irreducible polynomial, a monic irreducible polynomial of A. You know that the ideal generated by P and A, this ramifies in Km if and only if P divides M. This is exactly what goes on in the cyclotomic case. P will ramify in Q adjoins zeta M if and only if P divides M. We know that the Arden automorphism is determined by mapping lambda m to Cp adjoining lambda m, right? Just basically exponentiating lambda m by p, or the analog of exponentiation. And this is exactly what happens in this classical setting, in the number field setting. We get zeta m mapping to zeta m to the p, right? Moreover, we actually know exactly how primes split. A prime will split if f is the m-adic order of p, and we're assuming that p and m are co-prime in this case. If f is the m-adic order of p, then p is going to split into r. Oops, maybe I should decorate these with a little something. So maybe I should give these guys a flag or something to indicate that they're prime ideals in OM, right? So if you look at the type of ideal that P generates in OM, it's going to split into a product of R ideals where R is equal to phi of M over F. Okay. So for example, using this construction, you know exactly what primes say split completely in this extension. I guess they're all the primes what. So if we want this to split completely, I guess we need phi of M. We need F to be equal to phi of M. So in other words, what this means is that we need P to be congruent to 1 mod M. Those are specifically the primes that split completely. And we know from some, from algebraic number theory, I guess from more like class field theory, we know that there's a remarkable theorem where suppose you want to in some sense prescribe, you want to know what are all the extensions, given a number field, or given maybe even a function field, right? So given one of those, you want to know what are all the extensions. Can you describe all the extensions of a given field kind of intrinsically? As it turns out, you can. As it turns out, it's very much related to the behavior of primes. As it turns out, extensions of number fields or even global fields, these are determined by which primes split completely. So if you know in this kind of, they're just determined by which primes split completely. So say for example, you wanted to know, you just wanted to get a feeling for what kind of extensions there were of a given field. Well, as it turns out, in the number field setting and in the function field setting, these extensions are completely determined by the behavior of primes. And this works in the following way. Suppose you have two extensions where you know that the set of primes that say split completely in one extension is maybe very close, maybe up to a density 0 set, the same of the same set of primes that split completely in another extension. As it turns out, these two extensions need to be the same. I think this is a theorem of Bauer or something like that. But anyway, so this is wonderful. This basically means that you can kind of determine the ambient space, these ambient extensions. You can kind of determine them and talk about them without ever having to leave your little universe. You can describe them completely intrinsically just based upon what happens with the primes, right? And in particular, what primes split completely. So I guess the nice thing here in this kind of cyclotomic setting, it's like you know everything that there is to know then, and with respect to that, right? You know precisely which primes are splitting completely, right? And I guess the nice thing about this cyclotomic, these abelian extensions, particularly the cyclotomic ones, is that knowing what ramifies say, right? We know that P ramifies in Km if and only if P divides M, right? And this kind of these two things determine one another. And you notice that the primes that split completely, they would be precise, I guess by this line here, it would be precisely those primes P that are congruent to 1 mod M. So knowing the primes that split completely, or knowing the primes that ramify, tell you the right modulus to look at, which then kind of describes precisely what are the primes that split completely, right? So it's like this gives you like an explicit way to describe every single abelian extension of say, your rational function field, right? Well, maybe I jumped the gun there. In the number field setting, we know that this is true by Kronecker-Weber, and I imagine something is true in the function field setting.
It's a little bit of modification.
A little bit of one. But anyway, this is wonderful. It gives us and it's wonderful that that all this comes down to congruence. What could be nicer? right? I mean, you want to know, all right, what are the primes that split completely? Well, it comes down to what primes are congruent to one mod. Some modulus, which is determined by what ramifies, right? So it's very explicit, and it's very, it's just very tidy and very beautiful. I like it a lot. So, anyway. So yeah, very tight analog in almost every respect. These cyclotomic function fields are a very tight analog of the number field version, the cyclotomic number fields.